Hello everyone, and welcome to this webinar. This webinar will take a look at additive manufacturing and how DraftSight can be your CAD tool of choice for the manufacturing of 3D designs. My name is Brian Vanass, and I'm an application engineer for the DraftSight team here at Dassault Systèmes. I have about a decade worth of experience in manufacturing, and I look forward to talking to you today about this topic. Let's start off by going over what we'll be covering throughout this webinar. First, we will answer the question, what is additive manufacturing? Second, we'll take a look at the various types of 3D printing technologies that are available today. Third, we will see how additive manufacturing can provide value to a manufacturing company. And then finally, we'll understand how DraftSight can be a solution to your additive manufacturing needs with a demonstration on how you can design a part in DraftSight, starting with a 2D layout and then converting to a three-dimensional model. That design can then be exported from DraftSight to be sent to a 3D printer to build your part or your prototype. So, with that said, let's get into it. So, what is additive manufacturing? Well, additive manufacturing is really 3D printing. 3D printing being a synonym for additive manufacturing. They are two terms for the same process, which both mean the same thing. However, additive manufacturing is generally the term used by the industry. Now, additive manufacturing is different from traditional manufacturing or subtractive manufacturing, as it allows a part to be built layer by layer, whereas traditional manufacturing often requires a part to be made by removing material, sometimes a very large amount of material, to produce the desired part. Additionally, in traditional manufacturing, multiple parts might be machined or molded to be able to join the components together to achieve the final part. While in additive manufacturing, the final part can be constructed all at once. So, additive manufacturing / 3D printing is a manufacturing process that uses a machine, known as a 3D printer, to build an object with raw material from a computer-generated model file. With additive manufacturing, there are choices of materials to be selected to achieve certain mechanical and thermal properties for a part. Plastics being the most popular material choice. Two examples of thermoplastic polymers are PLA, polylactic acid, and ABS. PLA, with its low melting point and being biodegradable, can be used for quick prototype designs, where ABS, being a low-cost choice, can be used for components that require strength and flexibility, like toys, parts in automobiles, and so on. Then there is metal, like stainless steel, nickel, aluminum, titanium, bronze, or even gold. These metals are printed using a powdered form that are fused together using laser sintering to attain their hardness in solid form. The aviation industry is a large consumer of this method for ready-to-install parts. There is a use of graphite and graphene due to its strength and conductivity, used in electronics and lighting. Some examples being solar panels, touchscreens, or semiconductors. Another material is carbon fiber, which is used to help strengthen plastics. This allows for a fast and convenient alternative to metal. These are just some of the materials that are used in additive manufacturing. Some others include ceramics, abrasives, and biomaterials. Now, with the knowledge of the various materials that can be used with 3D printing, there needs to be an understanding of the different types of 3D printing technologies that are available to print these raw materials. So let's take a few minutes to go over the following list. The first technology, being one of the most well-known, is fused deposition modeling, or FDM. This is the method of extruding a plastic filament through a heated nozzle. The thermoplastic becomes molten when passing through that heated nozzle, allowing the printer to accurately place the material layer by layer until the part is completed. This type of 3D printer is what we'll be seeing later in the DraftSight demo. Next is stereolithography, or SLA. This was the first commercially available 3D printing technology. It works by curing a liquid photopolymer into the final part by tracing a high-powered UV laser in the shape of the part cross-section onto the build plate. This process continues while each subsequent layer is polymerized onto the previous one. The next type of printer is similar in technique to SLA. Being a resin 3D printing process, this is digital light processing, or DLP. This is where a light source cures an entire part layer at once by projecting an image of the layer cross-section onto the build plate. This in turn allows DLP printers to be faster than SLA printers. Up next, multi-jet fusion, or MJF, works by placing a layer of plastic onto the build plate. Then a heating head moves across the powder to preheat it. Finally, an inkjet type printing array moves over the powder and selectively places fusing and detailing agents onto the powder. The heating elements then fuse the layer. This technology allows for multicolor and multi-material components. The polyjet 3D printing process works very similar to the normal inkjet printing. The process consists of placing droplets of a photopolymer onto the build plate. A UV light then passes over this layer and solidifies it. The process repeats until a part is complete. Then there is SLS, or selective laser sintering. This works by placing down a layer of powdered plastic and tracing out the cross-section of the part with the laser. The laser melts the powder and fuses it. Another layer of plastic powder is laid over the previous one, and the laser melts the cross-section shape while also fusing it into the previous layer. Now, that was a lot on polymer or plastic 3D printing technologies. But let's finish this slide with two types of metal 3D printing methods. The first being DMLS, or direct metal laser sintering. The way it works is the machine places down a thin layer of powdered metal. Then a high-powered laser traces out the cross-section of the part and sinters the metal powder together. After each layer is completed, another layer of powder is deposited and the process is repeated. Finally, we have electron beam melting, or EBM. This is an advanced process where, as the name says, an electron beam is used to fuse the metal powder together. The printing chamber is kept under vacuum, so a high-energy beam can melt the particles together, creating a homogeneous microstructure that results in high-strength parts. Now, with all the information we just learned, from what additive manufacturing is, to the various materials that can be chosen to meet desired part properties, to the array of 3D printing technologies that can manufacture a part efficiently, leads to the question, why choose additive manufacturing? What value does it bring to the manufacturing industry? Well, let's take a look at the following. Complex geometries. 3D printing can easily achieve complex geometric designs. It accomplishes designs that cannot be made by either machining, stamping, milling, or injection molding. Almost anything you can imagine can be realized with 3D printing. Maybe you need internal cooling channels for turbine blades, or unique curvatures in a part for better aerodynamics. Well, additive manufacturing provides you with the flexibility and freedom to meet those needs. Now, this day and age, sustainability has become an important focal point for companies, and they're always looking for options. Well, additive manufacturing can meet those needs. Unlike in subtractive manufacturing, which can be seen in the following video clip, additive manufacturing builds a part layer by layer, wasting almost no material to complete the part, which reduces material waste. Parts can be designed to have the same mechanical properties, but lighter weight in design, in turn saving material and energy costs. Additionally, recycled materials or biodegradable materials can be used, while design parts for repair, refurbishment, and remanufacture, further enhancing sustainability. Next is weight savings. This falls in line with sustainability, where a part can be designed with internal lattice structures to reduce the overall weight of the part while still maintaining the desired mechanical properties like stiffness. This can be seen in the aerospace and automotive sectors. Or another example could be adding components in the part while printing, like additional wires, circuit boards, or small motors, so a completely separate part doesn't need to be built, which would add weight to the final assembly. This can be achieved because a 3D printer is able to pause during printing, allowing you to add these types of features. Up next is time savings. Time savings is another great value of additive manufacturing because parts are designed digitally using CAD software, like DraftSight. This allows you to design a part and quickly print a prototype to run tests like part functionality. If a modification needs to be made, time is saved by making changes to the CAD file and then print it again for retesting. Additionally, designers can build parts closer to the customer, reducing lead times and shipping times. Also, products can be made to order, allowing companies to take advantage of digital inventory, especially since you can make parts only as you need them. So, the final value I'd like to talk about is cost savings. Additive manufacturing cannot yet compete with the speed of, for example, injection molding, as can be seen in this short video clip. But what it can do is in the aspect of low volume manufacturing of less than 10,000 parts. Additive manufacturing saves costs on tooling. For example, with fewer parts, there will be less tooling in order for the part to be built. Not only does this save on costs, it also saves time, which reduces overall part costs. So looking at scale, the cost of making one part is about the same as making 1,000 of the same part. Before there was additive manufacturing technologies, low volume manufacturing was often very expensive. Now the choice is available. So, after all that, how does DraftSight apply to additive manufacturing? Well, as you can see in the diagram, 3D printing begins with an idea, a creative solution for a need or a function. That idea needs to be captured as a design or a model, so it can be sent to a 3D printer to bring it to life. Well, DraftSight can be your 3D modeling tool, allowing you to lay out your part dimensions in 2D and then convert to a 3D model, all in a single software package. With that said, let's now take a look at an example of a part being created in DraftSight and how it was sent to a Prusa i3 3D printer for construction. Alright, so here I'm going to start off by going to options, and I just want to make sure that I'm using millimeters as my dimensions. I go over and select millimeters, click OK, and I'm ready to begin to start drawing the lines. Here I already have a line drawn, a length of 140 millimeters. I'm going to continue drawing the rectangle. Here I am making a 45 millimeter length, going up 140 millimeters and across 45 millimeters, making the connection. Now I have my rectangle. So I have here my rectangle. I have already had two lines put in where I located the midpoint of the bottom portion of the rectangle and drew straight up 30 millimeters. I then continued to the right, connecting to the right side of the rectangle. Next, I typed in offset and entered in a 7 millimeter offset from the horizontal line inside the rectangle. I then wanted to quickly clean up the vertical line inside the rectangle. So I went over and selected Power Trim, where I could simply just swipe the cursor across that vertical line to remove it. I then want to select Circle with two endpoints to connect the two parallel lines. Then I select Power Trim again to remove the right-sided arc inside the parallel lines. I then want to round the corners of the rectangle. So I select the fillet command and I enter in 5 as the radius. And then I select the multiple entities to quickly round the corners. I then need to create a circle centrally located in the bottom portion of the rectangle. So I select the line, I find the midpoint of that bottom horizontal line of the rectangle and draw straight up. I then select a circle with the circle diameter. I find the midpoint of that line that I just drew. So then I want to expand out the circle. So I type in 15 millimeters for the overall diameter of the circle. Then I type in Power Trim to quickly clean up that vertical line passing through the circle. Next, I want to draw a second rectangle. I type line in the command window, and I perform the same tasks that I did earlier in the first rectangle. Then I need to create a entryway at the bottom of this rectangle. So I draw a line from the midpoint up 15 millimeters, and then I need to perform a offset where I set the offset 7.5 millimeters, and I'll offset to the left and to the right of this middle line. I then need to remove the lines in between the offsets, so I select Power Trim and quickly pass the cursor over the lines, removing them. I then want to create an arch between the two vertical parallel lines, so I decide to select the Circle command with two endpoints. Then I want to attach the DraftSight logo as seen in the left rectangle. I go up to Attach, I click on Image, I select the DraftSight logo I want from my files, I open it. Then I want to image trace this logo, so I select Power Tools, select Image Tracer, highlight the logo, and click OK. Next, I need to scale the logo appropriately to fit inside of the rectangle. I will highlight the logo and I will set a scale factor to 0.45. I will then rotate the logo to fit correctly inside of the rectangle. Next, I want to take this two-dimensional drawing and convert it to a three-dimensional model. I will change over to the 3D modeling function of DraftSight. I will then select Push-Pull command, and I will provide depth to this drawing. Once I am happy with this 3D model, I will export it as an STL file. The STL file will be sent to a Prusa slicing software, which will format it so then it can be uploaded to a Prusa 3D printer. As you finally can see, the part that I created using DraftSight to 3D model and then 3D print is an iPhone phone stand, incorporating the DraftSight logo into the phone stand. That was a great demo explaining how you can build a custom iPhone stand in DraftSight.
using DraftSight's functions to dimension the part in 2D, and then convert to a 3D model all in a single CAD tool. So with that said, let's recap on what we learned here today. Additive manufacturing is 3D printing. It is the terminology used in the manufacturing industry. Additive manufacturing is capable of achieving complex geometric shapes that cannot be achieved in traditional manufacturing processes. 3D printing allows you to quickly produce prototypes or ready-to-use parts in a cost-effective way. Additionally, by building a part from the bottom up, or layer by layer, there is little to no material waste. And finally, as you saw, DraftSight is a very capable CAD tool to meet all your 3D printing needs.
So, with that, I'd like to conclude with just one last slide, covering some of the resources where you can learn more about DraftSight itself. You can visit our website, DraftSight.com, where you'll find our product details for professional, premium, enterprise, enterprise plus, and 3D experience DraftSight. We also have a great variety of tutorials where you can learn the latest features and learn the fundamentals of DraftSight. Additionally, DraftSight also has a YouTube channel, so I highly recommend you check out the various videos of DraftSight and its capabilities.